Okay, hope all of you had a nice weekend and got some time to relax. So I hope all of you read my announcement. In case you did not, let me just remind you that we start our weekly test from this week onwards. It's the test one on sections 1.4, 1.3 and 1.4. On Thursday 20th. Okay, so I hope all of you know what time it is, and it's the time that you picked in your survey. So just go to Canvas, click on test one under modules. You should be able to see what time it is. Okay. All right. Before we start, do you have any questions about anything? So we just started with chapter 2, okay, last week. The first two sections are just two definitions that you need to know. There's nothing else there, okay, in terms of any problems to solve or anything. Sections 2.1 and 2.2 are pretty mild and easy going. So two things, let me just remind you of these two. You have two functions, y1 and y2. These are linearly independent. If one of them is not a scalar multiple of the other, if y1 is not equal to k times y2 of x, where k is a scalar. Okay, so we talked about typical examples of functions which are linearly independent. For example, if you have e to the power of k1x and e to the power of k2x are linearly independent if k1 not equal to k2. The same thing with sine and cosine functions for obvious reasons. Also, if you have e to the power of kx and x e to the power of kx, all these are examples of linearly independent functions, and these are the kinds of functions we're going to see today when we start solving second order equations. And again, no, these statements here are just based on observations. We know what these functions look like, and we know that this is not a scalar multiple of the other if k1 is not equal to k2. And if you have two of these, then for a second order differential equation of this form, ay double prime plus by prime plus cy equal to 0. Equal to 0 means it's a homogeneous differential equation. The general solution could be written as again, it's general because you have a bunch of constants which we don't know what they are. Okay, so the general solution would be y of x equal to c1 times y1x plus c2 times y2 of x, where y1 and y2 are linearly independent. Okay. In other words, you cannot write this just by repeating the same function twice. Okay, so if you write c1 y1 and then c2 times and the scalar times y1, that is not going to be enough, right? You need two functions which are distinct in its mathematical nature, and that is what we mean by saying they are linearly independent functions. So that's where we stopped, and that's all you need to know from sections 2.1 and 2.2. Okay. And the second thing is what we call as the principle of superposition. All right, so today we are going to really see how to solve for these things, okay, because on Thursday I showed you an example where I gave you the functions, asked you to plug it in and see if that was a true statement, okay, but that is not what we are going to do here. We need to really know how to solve these equations and get those functions out of the equation, okay. So today we'll be mostly doing section 2.3. If we get time, we'll just start on 2.4, okay. Solving second order homogeneous, and that means the right hand side is equal to 0. It's linear because there is no y square or y prime square terms, so I'm not going to write that explicitly. Second order homogeneous, constant coefficient. So we are trying to start with the easiest kind of differential equations and then see what kind of applications it'll have. And this is what it generally looks like: a y double prime plus b y prime plus c y equal to 0. A, b, c are all numbers, okay, because they are constant coefficients or real numbers. A cannot be equal to 0 because if a is equal to 0, the equation becomes first order. Okay. It's not a problem if b or c is equal to 0, that's fine, okay, but a cannot be equal to 0. Okay, so let's see the solution, what the solution to this looks like. Okay. Here's a question for you. So if you have a function y of x, okay, and if you take its derivatives y prime and y double prime, what kind of function from your experience so far will look pretty much the same in all these three terms? You know, they shouldn't change in its appearance except for some constant. Okay. They shouldn't be looking totally different at all. What kind of a function would do that kind of? What is it? All right, so some kind of an exponential function. Okay, so these will be the same. We put same within quotes because there could be a constant. Okay, so that's fine. These are the same if we pick your y of x to be some exponential function, so e to the power of rx. So r is a real number, or r is a number. Let me not call it a real number. Let's just call it just a number. Okay. That makes sense because if you take its first derivative, it's going to be r e to the power of rx. Okay. So let y equal to e to the power of rx, because then if you take the first and the second derivatives, it's still going to be exponential. Okay. That makes it sensible then that you could add them and get that equal to 0. So then you have y prime equal to r e to the power of rx and y double prime equal to r square e to the power of rx. And let's plug it into the equation. Okay, so now this is where the transition happens. We're going to change our second order differential equation into an algebraic quadratic equation. Okay, so you're kind of saying goodbye to calculus at this point. So we have a r square e to the power of rx plus b r e to the power of rx plus c e to the power of rx equal to 0. Okay, no more derivatives now, because we know a function that has to satisfy this equation should be an exponential function. If it was sine, it will change its function from cosine to sine back and forth. If you take the derivative, it is a polynomial, its degree will reduce by 1 when you take derivative. This is the only function that is going to stay the same. Okay. Well, let's factor out an e to the power of rx out of this. times AR square plus BR plus C equal to 0. And I hope all of you know this, that e to the power of Rx cannot be equal to 0. For whatever value of R you take, okay, the exponential function is always non-zero. And that leaves us with this equation here, because the product of two terms is equal to 0, at least one of them has to be 0. Okay. So we have AR square plus BR plus C equal to 0. It's almost like a metamorphosis. You started with this second order differential equation and you ended up with this second degree algebraic equation. Okay, that is the differential equation. This is the corresponding algebraic equation. This is what you call as the characteristic equation. So every time you start doing one of these problems in chapter 2, the first thing you do is write the characteristic equation corresponding to that differential equation. Okay, let's just abbreviate it as CE. Some textbooks also call it as the auxiliary equation because it just supports the calculation. Okay. So either way, it's a characteristic equation because it looks different, but it serves the same purpose of solving this equation here. Now you're back to your high school or middle school whenever you first saw your quadratic equation, right? All you have to do now is to solve that equation, which you have done a million times. So let's do that. So AR square plus BR plus C equal to 0. Roots are, I hope all of you know this, that there are two roots for any quadratic equation. Okay. Doesn't matter what A, B, C are, there are always two roots. And that's going to be negative B plus or minus the square root of B square minus 4AC over 2A. And please don't forget where we started this. Okay, we are assuming that y equal to e to the power of Rx is the solution. So we have two possible values for R, R1 and R2, given by the two roots of the quadratic. Okay. And all of us know that depending on the behavior of this term, the square root is going to be either going to give you two positive roots or one positive root or two imaginary or complex roots. So case 1, B square is greater than 4AC. So if B square is greater than 4AC, you're going to have a positive number here. Okay. So you have negative B plus or minus a positive number divided by 2A. So that means we'll have R1 not equal to R2. And both roots are real. Real means not imaginary or not complex. Okay. So all the numbers you know in this world are real numbers. Rational, irrational, fractions, decimals, all of them are real numbers. Okay. So we have two distinct roots or two unequal roots. So we can write our general solution. The y of x. Again, please look at where we started this. We started with y equal to e to the power of Rx. Okay. So since R is being represented by R1 and R2 here, we have C1 times e to the power of R1x plus C2 times e to the power of R2x, because R1 and R2 are both standing for R and they are not equal. Okay. So we have two linearly independent functions here, where e to the power of r1x and e to the power of r2x are linearly independent for r1 not equal to r2, okay, which is already here. We are doing it case by case. So at this point, we are not worried about what happens if r1 equal to r2. Okay, that's a different case, right? So if we have two real numbers which are not equal, representing the roots r1 and r2, it's a pretty easy situation there. The general solution is c1 e to the power of r1x plus c2 e to the power of r2x. All right, so let's do that example we did on Thursday. Okay. Just a quick example. Write the general solution for y double prime plus 5y prime plus 6y equal to 0. Now, you don't have to write stories about let y equal to e to the power of rx and so on. Okay, what you should do is start with the characteristic equation, which is the corresponding quadratic equation for this differential equation here. Okay, so that's where you should start. So the characteristic equation is r squared plus 5r plus 6 equal to 0. Okay. In this case, you don't have to even use the quadratic formula, right? You could just factor this into two terms as r plus 2 times r plus 3. Or r plus 3 times r plus 2. Doesn't matter. Those things are, you could commute these things without changing the answer. Okay. So there are two roots here. So you have r1 equal to -2 and r2 equal to -3. Once again, if you have questions like, oh, is it okay to call r1 as -3 and r2 as -2? Of course you can. Okay. Those things are irrelevant. You can flip these two as you like. Okay. All right, so now we have both the values, and you can write the general solution as y of x equal to c1 e to the power of -2x plus c2 e to the power of -3x. Any questions on this one? This is the easiest case. Okay, when you have two roots which are both not equal, then things are pretty easy. Again, I'm going to erase this, but please don't forget this part. Okay. Next, let's look at the case where r1 is equal to r2. So what happens if b square is equal to 4ac? Now you should be more careful, okay, because right now what happens is the square root of whatever is inside that becomes equal to 0. Okay. The square root of 0 is okay, that's just 0, but that just gives us one root, r1 equal to r2 equal to -b over 2a. Now, theoretically, we still have two roots. Okay. They are just repeated twice. So we have real repeated roots. It's wrong to say that the quadratic equation only has one root. Okay. There are two roots here, but you just write the same root twice. So according to what we have written earlier, the general solution should look like this. Y of x equal to c1 e to the power of r1x plus c2 e to the power of r1x, because r1 and r2 are the same. My question is this correct? Yeah, they're the same terms. Okay, you just change C1 to C2. I could call this C5. Who cares? Okay, these are the same functions, so this is not right. Okay? Please don't do this. So we need something to replace the second term here. Okay, so this is wrong because we have linearly dependent terms because this is just a scalar multiple of this. Okay. Linearly dependent functions, which is not going to complete the solution. Okay, one of those terms is correct, but writing C2 instead of C1 is not going to save you. Okay, that is not going to work. So what should we do here? So we have a small theorem that will help you get the second function that is going to complete the solution. Okay. So I don't expect you to do derivations on tests and things, but I just wanted you to know how this thing is derived. Okay. So if you're not interested in derivations, you could probably just pay attention or, So here is a theorem that I'm going to use. If y1 of x is the solution, which is what we have, okay, for y double prime plus p of x times y prime plus q of x times y equal to 0. Slightly different format here with the leading coefficient equal to 1, okay, but that shouldn't change the story. The second linearly independent function solution is given by, let me just make some room. All right, it's given by y2 of x equal to y1 of x times the integral of e to the power of negative integral of p of x dx. Okay, that looks like our integrating factor divided by y1 of x square dx. So it's a big integral that covers this entire thing dx, okay, and that entire thing has an integrating factor. So that is why there's an integral here, integral there. Okay. I'm not going to derive this to derive something else. So this is what Abel's theorem looks like. Okay, Abel derived this at his own leisure time. So we're just going to borrow that result here. So what did we have? Our equation was this. A y double prime plus b y prime plus cy equal to 0. Okay. We need to convert it into that form there, y double prime plus p of x y prime plus q of x y. So you divide throughout by a, and you get y double prime plus b over a times y prime plus c over a times y equal to 0. So that your p of x is b over a. Now you already know that one of the roots is given by that R1 equal to R2. Okay. So we already know this one. y1 of x equal to e to the power of r1x, which is e to the power of negative b over 2a times x. That is based on what I wrote up there. So what we are trying to do is make use of this information here and our p of x to get the second linearly independent function that is going to give you the solution to this case. So let's plug it in. So this is going to be y1 of x, which is e to the power of negative b over 2a times x. So that thing is outside of the integral times e to the power of negative integral of p of x is b over a. Okay, b and a are numbers. So this is b over a dx divided by y1 of x square, which is going to be this term square. Okay, e to the power of negative b over 2a times x square dx. But that looks complicated if you just look at it once with the too many things going on. Okay, but it's not actually that bad if you just calmly simplify it. It will come out to be something pretty nice. Right? When you erase this part, which is where we started this whole thing. Okay. Okay, so let's simplify this. This is going to be e to the power of negative b over 2a times x, which is our existing solution or existing root, times the integral of e to the power of negative b and a are numbers. You can pull that out. The integral of dx is 1 dx. So it's going to be just e to the power of negative b over a times x. That's because the integral of dx is just x. Now this one, I know it looks complicated, but all you have to do is just cancel these twos. Yes, you write the square root of something that is actually to the power of 1/2. So this 2 and that 2 cancels out. Okay. And you get e to the power of negative b over a times x in the denominator dx. And if you look closely, those two terms are the same. They cancel out. That leaves us with 1. So it's going to be e to the power of negative b over 2a times x times the integral of 1 dx. And that is x, right? Integral of 1 is x. So it's going to be x times e to the power of negative b over 2a times x. So the point of doing this whole derivation is that if you know, for the repeated root, if you know one of them, okay, you can always multiply an x to it and get the second linearly independent function. So those of you who don't want to look at derivations, this is what you need to know. So for case 2, the general solution is given by y of x equal to c1 e to the power of r1x plus c2 x e to the power of r1x. Again, the value of r1 should be something that you get out of the quadratic. So there is nothing unknown about r1. Okay. The only thing you need to keep in mind is to not forget this extra x here. Okay, that is what keeps the second function linearly independent from the first one. Okay, so please don't forget this. So the first time I taught this course, I just wrote this as a result, and then a lot of students asked, well, how do we know that, multiplying x would, and that's why I started doing this Abel's theorem, so that it's convincing to everyone that this is the only way to do it. Okay, yeah.
So what about the plus C?
Plus C where? That C is here.
That's C. Because when you solve integral of 1 to x, that's x plus C.
Yeah, that C is here.
Oh, that's C. Okay.
Yeah, all the C's are here. Yep. There are C's there, here, all C's are there. Okay, so no need to worry about any extra constants here. Any questions about this? So this is slightly trickier than case 1. Okay, as long as you don't forget this extra x, you're not dealing with anything too complicated, but okay, this is the key thing. All right, let's do an example. Sample solve or write the general solution to for y double prime plus 4y prime plus y equal to 0. Once again, we start with the characteristic equation. It's 4r square plus 4r plus 1 equal to 0. Maybe you could factor this, okay, if you are good with identifying things in a quadratic, or you could just use a quadratic formula that is safe. Okay. That's negative b plus or minus the square root of b square, which is 16, minus 4ac, that is also 16, divided by 2a, which is 8. Okay. So if you were to factor this, it will look like this 2r plus 1 times 2r plus 1. If you don't want to take chances and make mistakes, the quadratic formula is always reliable. Okay. So this is 0, and that's going to give you negative 4 over 8, which is negative half. Okay. That's what you would have gotten from here as well. R1 and R2 equal to negative half. Okay. So the general solution is given by y of x equal to c1 e to the power of r1x, which is e to the power of negative 1/2 x or x over 2, whatever you like, plus c2 e to the power of negative 1/2 x. I don't know, I left a gap there. I don't know why. X. Yeah. Throughout chapter 2, whenever you write a general solution, make sure that you're writing linearly independent terms over and over. Okay, please don't just take one term and multiply it with a number and write more terms. That's not going to help us. Okay. So c2 x e to the power of negative 1/2 x. All right, so case 1 was R1 not equal to R2. Okay. Let's just make a list here. Case 1, R1 not equal to R2, but both of them were real. And in that case, you had y equal to c1 e to the power of r1x plus c2 e to the power of r2x. You can see that here. In case 2, if R1 equal to R2, of course they are real. Okay. And in that case, you have y equal to c1 e to the power of r1x plus c2 xc to the power of r1x. You're going to make use of this throughout chapter 2. Okay, so that's why I'm just making sure that all of you understand this process. And you see that when I'm doing this problem, I don't really say anything about Abel's theorem or anything. Okay, you don't have to worry about all that stuff. Any questions on this? Oh, I think there's a question there. We will need two initial values. So I'll do initial value problems once I list all three cases. Okay. So in some cases it's easy, some cases you have to do some work. So I'll do examples where you have to find C1 and C2 after I finish cases 1, 2, and 3. Okay, so, but yeah, that's a good question. All right, one remaining case, case 3. This is where all the magic happens. Okay. All the beauty of the solutions comes in when you have R1 not equal to R2, but both are imaginary. And based on, I'll write down why we are worried about these imaginary roots and so on. Okay. Now, if you've never seen imaginary numbers in your life, don't worry. This is all you need to know. Okay, so we are solving AR squared plus BR plus C equal to 0, and the roots were written as R1, R2 equal to negative B plus or minus the square root of B squared minus 4AC, whole thing divided by 2A. And I hope all of you realize that the only remaining possibility here is that if B squared is less than 4AC, that is when it becomes negative. You cannot find the square root of a negative number. You take a calculator and do it. It's going to give you error. Okay. So we need to define something, and that is why mathematicians came up with this clever idea of defining I being the square root of -1. Now, if you're an electrical engineer, you probably use J here because I is electrical current for those people. Okay. So anyway, so we will stick to I. So I is the square root of -1. You can write this as negative B over 2A plus or minus I times the square root of, now you're going to swap these two, okay, 4AC minus B squared divided by 2A. Because you're taking a -1 outside the square root, and that is what we are representing by I. Okay. So there is a real part here. Let's call this P, and let's call this part as Q. Any quadratic equation will either have both real or both imaginary. You cannot have one real and one imaginary because of the way this square root comes with a positive and negative at the same time. Okay. So this is of the form P plus or minus IQ. So the nice thing is that you have both P and Q being the same, just a sign that changes for all these roots. Okay. And we are interested in finding, remember that A, B, C were real numbers. Okay, so we are taking a real world problem and then trying to do this, and suddenly we get hit with these imaginary numbers. We don't know what to do. Okay, that is where we had to be clever. So we are interested in finding real valued functions, linearly independent functions, satisfying A y double prime plus B y prime plus C y equal to 0. This is what we are trying to achieve here. Okay. Because I is part of the process, but you cannot just say that, oh, the roots are imaginary, so it's useless. Okay. These are probably the most useful of the three cases. So please, we need to somehow find real valued functions out of this hopeless situation. Well, when mathematicians first introduced this idea of imaginary numbers, okay, it looked like a pretty crazy idea because who wants to think about numbers which are not real? And then came a very smart person who was to make this extremely useful for all kinds of applications. His name was Leonhard Euler. This thing single-handedly changed the applications of mathematics, especially when it involved imaginary numbers, identity. Yeah. Just look at the identity, it looks like this. E to the power of I theta is equal to cosine theta plus I sine theta. Remarkable that he could take an exponential function and write it in the form of a cosine and a sine function, which is both periodic and oscillatory. Okay, because an exponential function, if you think about it, it's either going like this or going like this. But somehow he claimed that if you do some manipulations, you could write it in the form of cosine and sine. It's not very difficult to show this, okay, because if you look at the Taylor series for all these functions, Euler couldn't just claim things out of nowhere. There has to be a reason why these things are true. Okay. The Taylor series for cosine of theta is theta minus, write this carefully, 1 minus theta square over 2 factorial plus theta to the power of 4 over 4 factorial. One question that engineers always ask is, who cares about all these things? This is the time we need to start caring. Okay. The reason why these things become useful is because of really deep-rooted concepts like this. Okay. So Taylor series for cosine is this. Sine of theta is theta minus theta to the power of 3 over 3 factorial plus theta to the power of 5 over 5 factorial. So on. Okay. You've probably done this in calculus too, Andrew, but of course, each time you did this because it looks so abstract and complicated. But all you're doing is taking those functions and writing it as polynomials, okay, which means it's just a sum and difference of a lot of functions. And the magical thing about I is that I is the square root of -1. So I square is -1. I to the power of 3 is I squared times I, okay, which is negative I. I to the power of 4 is I squared times I squared, which is +1, and so on. Okay, it goes in circles. Okay, now we are getting somewhere. Okay, something that looked arbitrary is now defining what you would have expected in a unit circle. Okay. You started with I and you're back to 1, okay, and it keeps going in. Another I to the power of 4 would bring it back to 1. That is what happens in a unit circle, right? It starts at 1, 0, goes around, comes back here. So I times sine theta. Take this, multiply by I on both sides. You get I theta minus I theta to the power of 3 over 3 factorial. I theta to the power of 5 over 5 factorial, and so on. Let's simplify this. This is going to be I theta. I to the power of 3 is minus I. So it's going to be minus negative I theta to the power of 3. I to the power of 5 would be I to the power of 4 times another I. Okay, that's going to be plus I theta to the power of 5, and so on. So the good thing is that the I kind of factors out of all these. Okay. So this becomes I times theta plus theta to the power of 3 plus theta to the power of 5, and so on. Now if you add cosine theta and I sine theta, you get 1. I'm going to write this in the order of terms. Okay, so 1 plus I theta, that's this term. Then you have minus theta square over 2 factorial plus I theta to the power of 3 over 3 factorial. This is still here. Sorry. So that is going to be the cosine theta term, okay, and plus I sine theta, which is going to be coming from here. Okay, so it's going to be plus theta to the power of 4 over 4 factorial. That is this term. Then you have plus I theta to the power of 5 over 5 factorial. And e to the power of I theta, if we use its Taylor series, e to the theta is 1 plus theta square over 2 factorial. And if you replace this theta by I theta, plus I to the power of 3, theta to the power of 3 over 3 factorial. And if you compare this term by term, e to the power of I theta and cosine theta plus I sin theta, you would see that 1, I theta, okay. You have I square, which is -1. Okay. So you have negative theta square over 2 factorial, which is here. I to the 3 is I, right? And that is what you have here. And so on. So those terms are exactly the same thing. So we have e to the power of I theta equal to cosine theta plus I sin theta. If you're an engineer, this is probably the first of the million times you're going to see this thing. You cannot survive engineering without this magic identity. Okay, it's called Euler's identity. It's very famous, very useful, because what it does is it takes a seemingly impossible thing like e to the power of I theta and brings it down in terms of two very useful functions. Okay. It tells you that this function is oscillatory in nature, cosine and sine. You don't need the derivations. Again, I'm showing you this because, this is how mathematics evolved. People thought it was useless. Then like, oh, actually this is pretty clever. I'll show you one more thing based on this, and I'll keep continuing with what we are doing. Okay. What is e to the power of I pi? If you replace your theta with pi, okay, you have cosine of pi plus I sine pi, where your theta is in radians. And I hope all of you remember that sine of pi is 0, cosine of pi is -1. In other words, if you add 1 to e to the power of I pi, it's 0. It's supposed to be the most beautiful mathematical equation on this planet or the universe. Okay. The reason for that is because all the three mathematical constants, E, I, and pi, they are all together in the same place. Okay. And you add 1 to it, you get 0. It's a conserved quantity. Okay. Remember, this pi came out of a circle. I is an imaginary number. E is the Euler's number. Okay. Somehow they are all related by just 1. So that is supposed to be one of the most beautiful, or the most beautiful equations written mathematically. Okay. But you could disagree with that one. I don't have a problem. So the reason why this is going to be helpful for us is because we had R1 equal to P plus IQ and R2 equal to P minus IQ as our two roots. And the general solution would be y of x equal to c1 e to the power of r1x. Let's call it as k1. Okay. For a different purpose. So k1 e to the power of r1x plus k2 e to the power of r2x. Don't forget about what we are trying to do here. We are trying to get two linearly independent functions that satisfy the original differential equation, which was a y double prime plus b y prime plus cy equal to 0. We're trying to get two real valued functions, no I in the answer. Okay? That is what we're trying to achieve here. So we are halfway down there. We need to clean it up. Okay? So this is going to be k1 times e to the power of r1x, which is p plus iq times x, plus k2 times e to the power of p minus iq times x. I'm doing this slowly so that you see how these things evolve. Okay, I could have just written the answer, but then that's not how things should be done in mathematics. Let's use a very simple law of exponents here. This is going to be k1 e to the power of px times e to the power of iqx plus k2 times e to the power of px times e to the power of negative iqx. The e to the power of px term is common to both these terms. Okay. So we can write this as e to the power of px times k1 e to the power of iqx k2 e to the power of negative iqx. That's a perfect spot for using Mr. Euler. Okay, just you have e to the power of I theta, theta is qx. Okay, and you have that here and here. The only difference there is a negative sign, which you can just negate it in the middle term. Okay, that's going to be e to the power of px times k1 cosine of qx plus I sine qx plus k2 times, I need to be careful with my brackets here. Okay, so this e to the power of px is multiplying the whole thing plus k2 times cosine of qx minus I sine qx. In case you're wondering how that happened, e to the power of negative I theta would be cosine theta minus I sine theta. That's because cosine of negative theta is same as cosine theta, and sine of negative theta is negative sine theta. Because cosine is an even function, sine is an odd function. So for that reason, the sign of cosine does not change. The sign of sine changes. Okay. Now let's try to separate this in an efficient way. Okay, so it's going to be, so if I keep my I terms and the non-I terms together, this is going to give you k1 plus k2 e to the power of px times cosine qx. So that's my non-I terms, also called the real terms. Plus, the next term is going to be a little bit tricky because it's got this I in it. Okay, you need to be kind of cleverly removing that out of the picture at this point. Okay, so we have ik1 minus ik2 times e to the power of px sine qx. I'm putting this parenthesis here so that you want it as sine q times x, okay, sine of qx. At the risk of repeating myself, we are looking for real valued functions. We have achieved that goal. Okay, just need to call this as C1 and this as C2. So your y1 of x is this block here, e to the power of px times cosine qx. y2 of x is this block here, e to the power of px times sine qx. Okay. Now there is always this nagging question, what do you do with that I? I just throw it away. Okay. We don't need it. We don't need it because we're looking for real valued functions. Okay. So this I served its role, moved out of the picture. Okay. We don't want to keep bringing it back and complicating things. Okay. So C1 and C2 are two constants now. There are some students who spend the rest of the semester trying to think about this K1 and K2. Okay, that is none of our business at this point. Okay, we tried to find those two functions and we have what we need and we need to keep moving. The general solution to case 3 after a long derivation. In case 3 is where R1 not equal to R2, both of them are imaginary. Okay, R1 is P plus IQ and R2 is P minus IQ. Or you could call it the other way, I don't care. Okay. It's given by y of x equal to C1 e to the power of px times cosine qx plus C2 e to the power of px times sine qx. It tells you that these functions are oscillatory in nature. Okay. You can factor e to the power of px if you want to and write it as C1 cosine x with C2 sine x sine qx. Should we worry about what K1 and K2 are? No. Okay. We only need to worry about C1 and C2. That is what will decide the general solution. And both these functions are independent of I, which means they are real valued. And we couldn't have done this without Mr. Euler, so you need to be indebted to him. So note, if P is equal to 0, that could happen. Okay. We have y of x equal to C1 cosine of qx, C2 sine of qx. There is no e to the power of term because it's e to 0, which is 1. Okay. This is oscillatory, this is oscillatory. What you have is then a function that looks like this. Remember the graph of sine and cosine, they kind of superimpose on each other and gives you a net oscillatory function like this. Okay. This is what you call as a simple harmonic motion. Some of you would have seen this in physics already. Okay. Simple harmonic motion, it also happens in electrical engineering with signals which are oscillating at the same frequency and amplitude for the entire time. Okay. What if P is positive? So you have e to the power of px times C1 cosine of qx plus C2 sine of qx. It's not really oscillating, but it's also exponentially growing here. Okay. Instead of steady oscillations, what you get is oscillations that start slowly and kind of go crazy like this. Steady climbs up because of this. It's an exponential growth. That's a bad one because if you are dealing with a real physical system, that means your oscillations get so wild that at some point it's going to break. Yeah. And if P is less than 0, the same solution, what do you think the graph would look like at this point for P less than 0? Any guess? This is a graph for p greater than 0. That was for p equal to 0. Yeah.
It becomes smaller in size.
Yes. So just instead of exponentially growing, it's going to exponentially decay with respect to time. Okay. Like this. That's not too bad, right? Because it starts, that's what happens if you just compress a spring and let go, the oscillations that eventually die down. All right, so the behavior for R1 not equal to R2, both imaginary, it might look like it's the most unreal thing, but it's actually the most real thing because of these oscillations. So let's do a couple of examples and then we'll mix it up and do a few problems. Okay. Examples for case 3. Y double prime plus 25y equal to 0. There is no y prime there. Okay. That's purposefully done. So y double prime plus 25y equals 0. When you write the characteristic equation for cases like this, be careful. Okay. The first one corresponds to y double prime. The middle one is absent. The last one is your constant term. Okay. So we have r square plus 25 equal to 0. So you can solve for r square equal to negative 25. You don't have to use the quadratic formula here. You could. That's an overkill. Okay. R square is negative 25. R equal to plus or minus the square root of negative 25. Okay. If you've never done imaginary numbers in your life, this is what you would do. Okay. You have r square equal to something. R would be plus or minus the square root of that thing. That is where we have plus or minus 5i. So there is no p there, right? P is equal to 0 and q equal to 5, not 5i. So p equal to 0 and q equal to 5 gives you, this is case 3, obviously, and that will be y of x equal to c1 cosine of 5x plus c2 sine of 5x. We'll give a physical meaning to this maybe later today or tomorrow, what that 5 means and so on. Okay. Right now, that is what the general solution is. And I hope all of you observe there is no I in the answer. Okay. This one more, y double prime plus 6y prime plus 52y equal to 0. So this one has all the terms a, b, and c. So the characteristic equation is r square plus 6r plus 52 equal to 0. I don't think you can factor this. You have to use your age-old quadratic formula here. So it's negative b plus or minus the square root of b squared minus, just if you may pardon me for 1 minute, just change this 52 to 13. Okay. I expected the 52 the next step. I'm sorry about that. My bad. Kind of jumping a little bit ahead of myself. 4 times 13 is 52. That's the risk of making examples on the go. That's -6 plus or minus the square root of 36 minus 52 is -16 divided by 2. Doing this slowly so that I'll show you some mistakes that I see on exams and quizzes. Okay. That's -6 plus or minus 4i. Square root of 16 is 4, square root of -16 is 4i, okay, not -4. And for some reason, after so many years of math, okay, students do this. Is that right? Like, oh yeah, that's right. Is that right? What is wrong? Yeah, when I'm being unfair to Mr. 4 here, okay, and if I'm canceling it, I should cancel it on both the terms. Yeah. I hope at this point I don't have to give you a tutorial on why this has to happen or cannot happen. Okay. Please don't make that mistake on exams. It'll change your answer in a lot of unpleasant ways sometimes. So that's why you need to be careful about small things. So we have P equal to -3. And Q equal to 2. And case 3, which I just wrote there, would be y of x equal to e to the power of -3x times c1 cosine of 2x plus c2 sine of 2x. So that is a full problem. So the first example was kind of convenient because the b term was absent. Okay, it gave you a simple harmonic motion. This one is oscillating at the same time, it's exponentially decaying with time. So those are the 3 cases that is going to kind of decide your course in chapters 2 and also in 3, but then 3 we are going to use a different technique. So there everything will fall under the same thing. Any questions about case 1, 2, and 3? I'm going to just throw a few examples at you now. Try to do it yourself. Okay? But before I do that, do you have any questions? What about people online? Any questions? Again, I won't ask you to derive Euler's formula or Abel's theorem or anything. Okay. These are the 3 things you need, case 1, 2, and 3. Keep it handy and do your math carefully. Don't do illegal things like this. Okay. You should be good. All right, here are a few examples to work on. And I also throw some initial value problems in there. So exercise or examples. So the question is to solve. Okay, in some cases, write the particular solution, or in some cases, write the general solution. So y double prime plus 2y prime equal to 0. It's kind of mixed and matched, so I don't know which case it is right now. So maybe I know, but I'm not telling you. 3. Okay, so 5 problems. I think it has at least one of each case. Okay, so take your time, do this, and I will follow up a few minutes later. And people online, feel free to ask questions by unmuting if you have any. Okay, so don't hold back any questions. I may be wrong. Okay, you have to correct me if I'm wrong. So, what is wrong? 2R. Okay. If all the 3 terms are there, it's easy. If only 2 are there, just be careful. Which you don't know which ones are there. The R square is always there, otherwise it's first order. Okay. To solve this, you don't have to use any nuclear weapons, so just do this. Okay, you could use quadratic formula, but you don't have to. Okay. And it's possible that I'm wrong. Okay. For some reason, I only have 1 term in the solution. Is that right? This is a 0. Who cares? Plus C1, right? You should care because e to the 0 is not 0, it's 1. Okay, so it's C1 plus C2 e to the negative 2x, and this is going to be C1 e to the 0. Okay, you don't have to write e to 0 explicitly. Okay. You should always have 2 terms when you write the general form. Okay. Good. Is that what everybody got? Any questions? Case 1 is easy if you don't do any unnecessary mistakes. Okay. Case 2, sorry, problem 2, I didn't say case 2, problem 2. R square plus 36 are equal to 0 or not? No, right? It should be r square plus 36 equal to 0. The square root of 36 is not 18, it's 6. Okay. Now equal to plus or minus the square root of negative 36, which is plus or minus 6i. And those of you who find it helpful to write which case it is, you can write case number 3 in this case. Yeah. Is there something not nice with any of the numbers given? Or everything is okay, right? Okay. I don't know, I just wrote those things, so if anything comes out to be weird, just let me know. So this is case 3 with p equal to 0 and q equal to 6. Simple harmonic motion, so it's going to be y of x equal to c1 cosine of 6x plus c2 sine of 6x. But here, this is not the end of the problem. We are given two conditions there, y of 0 and y prime of 0 to solve for c1 and c2. And if you can remember these values here, that will be great. Cosine of 0 is 1, sine of 0 is 0, okay, in radians. Even in degrees, that's the same thing. But so y of 0 is c1 times cosine 0 plus c2 times sine 0. If you want, you can write that. And since sine of 0 is 0, we have c1. That is given to be equal to 1. Now we are locking in on a unique solution. It's no longer arbitrary C1 and C2. We got C1. To find C2, we need another condition, the initial velocity. So y prime of 0, y prime of x first. So take this function here, take its derivative with respect to x. That's going to be negative 6 C1 sine of 6x plus 6 C2 cosine of 6x. Hope all of you know where that 6 comes from, the chain rule and all that stuff. And if you put y prime of 0, you get 6 times C2. Again, because sine of 0 is 0, cosine of 0 is 1. And I gave you that equal to 2. So C2 equal to 2/6 or 1/3. Now we have a unique solution for that particular set of conditions given to you. I don't want to erase the problem, so we just try to squeeze it somewhere in here. So y of x using the C1, C2 values would be cosine 6x plus 1/3 sine of 6x. Now it's okay to call it a C1 sine of x plus C2 cosine. If you change it, then you have to change a whole bunch of things later. So it'll be nice if you just stay with what I'm doing in class so that it's easy for you to compare your notes and solutions later. Okay. So I'm writing always cosine first and sine second. Okay. But that's just a choice thing for convenience. Any questions on these two problems? Let me know if I'm going too fast. Okay. All right, number 3. start with the characteristic equation. Nothing tricky here. There are three terms, so just write r square r and no r. Okay, so r square plus 10r plus 25 equal to 0. All of you know how to factor this. R plus 5 times r plus 5 equal to 0. We have two real roots, but they are the same roots. So this is case 2. R1 equal to R2 equal to -5. In case you're wondering what case 2 is, it's written there. And the general solution is y of x equal to C1 e to the power of -5x plus C2 x e to the power of -5x. That's the general solution. Now we need to find C1 and C2. So we're given y of 0 equal to 2. Now there is an x here, that is a convenient one. If you plug in 0 here, that whole thing will disappear. Okay, so you get C1 equal to 2. And you need to find y prime. So the derivative of the first term would be -5 C1 e to the power of -5x plus C2 times the derivative of x is 1 and it's e to the power of -5x. Do you see anything wrong? Or let me see how. What do you call that rule? Product rule. Okay. Don't forget to do product rule if you have multiple terms. So this is one of the terms. And then you have C2x times the derivative of this, which is -5 C2 x e to the power of -5x. So if you forgot the product rule, please go and review it. Nothing fancy there. And now you can plug in 0. Please don't plug in 0 and then find the derivative. Okay. Find the derivative, then plug in 0. That is obvious. Y prime of 0 equal to -5 C1. Don't forget, we already know C1. Okay. So it's -5 C1 plus C2. Again, you're plugging in x equal to 0 in the third term, so that one disappears. And this is going to be equal to 3. C1 is 2. And you get C2 equal to 13. So the particular solution for this problem would be y of x equal to 2 e to the power of -5x plus 13 x e to the power of -5x. Any questions up to there? All of you are getting comfortable with this material? Yeah. Or just going above your head? Okay. You need to tell me, okay, if I'm going too fast, just let me know. Okay, number 4, which is usually something that students kind of overcomplicate without any reason. I have to erase the whole thing because I need some room. It's r square minus 9 equal to 0. It's y double prime minus 9y, not y prime. So it's r square minus 9. Okay. To solve this, you don't have to do anything fancy. Just factor this into 2 terms using your a plus b times a minus b thing. Sometimes students use the quadratic formula, which you could do that, but you have to do it carefully without making mistakes. Okay. It's easier if you just factor it this way because it's a minus in between. This is why I said some of those algebraic things you did earlier would be very handy. Please don't change the middle sign to a positive and think that will change it here as well, only for negative. Okay. All right, so we have, which case is this? Case 1, 2, or 3? Case 1. Okay. Three and negative 3 are not equal, so please, it's case 1. All right, so we have y of x equal to c1 e to the power of 3x plus c2. Yes. First, now need to put an x in front of this. Okay. This is case 1. Because negative 3 and 3 are not the same. All right, plug in the conditions. Now we're going to get 2 equations to solve this. Okay, so y of 0 equal to 0. Oh, sorry, y of 0 equal to 0. Give you c1 plus c2. E to the power of 0 is 1. So we have c1 plus c2 equal to 0. That's an easy one to use because you can write c1 equal to negative c2. Or c2 is negative c1. Okay. Y prime, just need to take the derivative. 3c1 e to the 3x minus 3c2 e to the power of negative 3x. And c1 is negative c2 or c2 is negative c, whichever you did. You can plug it in here. And you're plugging in x equal to 0, so y prime of 0 would be negative 3c2 minus 3c2, that's negative 6c2 equal to 5. So c2 is negative 5/6. Can c2 be negative? Of course. And c1 would be then negative of negative, that's positive 5/6. So you don't need any advanced linear algebra to solve this, even if you have 2 equations. Okay, they are easily doable. So you get y of x equal to 5/6 e to the power of 3x minus 5/6 e to the power of negative 3x. That leaves us with the last one, which is probably the longest of them all. Okay, this case number 3, I hope, and it's also got a set of initial values. Okay, and you would see that this later on when we do the spring mass problems, it takes a little bit of time to do the whole thing. So please practice these problems a lot so that you won't run out of time on tests. Okay. Can you erase this thing? Any questions? I need some room here. All of you online okay with this? Slowly encroach into this. Number 5. It's perfect. I think once we're done with this, we'll be done with today's lecture. So nice way to end it. So we have r square plus 2r plus 2 equal to 0. I don't think you can factor this. So we have negative b plus or minus square root of b square minus 4ac, that's going to be 4 times 2, 8 divided by 2a. That's negative 2 plus or minus the square root of negative 4. Okay. I do this in so many steps so that I won't make mistakes. So you don't have to jump 5 steps and show that you're able to do this all without. Just do it slowly. Okay, so that way you don't have to go back 5 steps and correct your things. 2i over 2. Think showed you this once. Okay, hopefully all of you remember, if you're canceling something, cancel everywhere or nowhere. And that's equal to negative 1 plus or minus I. So P is negative 1. Q is 1, okay, not I. Okay, so case 3, which is right here. The general solution is y of x equal to e to the power of negative x times c1 cosine of x plus c2 sine of x. Q is 1, P is 1, P is negative 1. Okay, so all right, let's plug in the conditions. Y of 0 is e to the 0 is 1, c1 times 1, c2 times 0. So it's just c1, and that's equal to 0 from what is given here. Okay. So tomorrow it will mean something when we do the spring mass problem. It says that the initial displacement is 0. Okay. So that's okay. And told you earlier about the product rule. Okay, here it's going to be a little bit more intense because of the exponential and the sine cosine terms. So do it carefully. So you can do it whichever way you want. So the derivative of the first term, which is negative e to the negative x, times the second term, which is c1 cosine x plus c2 sine x, plus the first term times the derivative of the second term, which is negative c1 sine x plus c2 cosine x. It's not difficult, you just need to write it out. Okay. And then you plug in, well, we already have c1 equal to 0. Okay. And e to the 0 is 1. So what we have when you plug in 0 is y prime of 0 equal to, well, sine of 0 is 0. Okay. And we have just c2 here. And I gave it to you as negative 1. So c1 is 0, c2 is negative 1. So the particular solution, or the unique solution for this would be y of x equal to negative e to the power of negative x times sine x. Because c2 is negative 1, and when c2 is multiplying the sine term. Okay. All right, nice. So that's a nice place to stop. We have 5 minutes remaining. So tomorrow we'll start 2.4. We'll look at an application of this based on spring and mass, okay, and try to give some physical meanings to these terms. All right. In the meantime, don't forget about test number 1 on Thursday that covers what we did last week. Okay. That's it for today. So take care. Stop recording.
Thank you.
Thank you.